Hello, my name is Jesus Ramos, and this is my final presentation for BME 325, and we will be talking about the Stokes-Einstein equation. So, how is this equation derived? So, our first, we will get to know our authors, Albert Einstein and Sir George Stokes. So, now we'll talk about the Einstein-Stokes equation in parts. So, D is equal to the diffusion coefficient. Mu is our solvent viscosity. R is the radius of the solute, and then T is temperature in Kelvin, and then K sub B is the Boltzmann constant, which is 1.38064 times 10 to the negative 23rd power joules over Kelvin. So now we'll talk about the Navier-Stokes equation. So when we diverge spherical polar coordinates, we first get the equation to our right. Individual velocity components are in two equations, which are the Q sub r and Q sub naught equations. When combining both velocity components, we set it equal to 0, and then we get the following equation, as you can see, is equal to 0. We can see that in both radial and polar velocity, the velocity components are equal to 0. So when r is equal to a, Q sub r is equals to 0, Q sub theta is equal to 0, and once again r is equal to a. So keeping the boundary conditions in mind, we can assume that the following equation is true, in which the coefficients are defined by f of r. And so psi of r theta is equal to f of r times sine square theta. So we notice that f is governed by the equidimensional differential equation, which is the equation shown below, where d squared over dr squared minus 2 over r squared, and this whole section squared times f is equal to 0. The solutions are from the form f of x is equal to r to the n power. The following equation for f of r is shown down below. So when we substitute the f of r equation into the phi equation, we get the following general equation. As seen, psi is equal to sine squared theta times the whole section, a over r plus b times r plus c times r squared plus d r to the fourth power. So to satisfy the boundary conditions at an infinity point, and knowing r is equal to a, we set both d equal to 0 and c equal to u over 2. Using the velocity component equations, we solve for a and b. And we get a is equal to 1/4 WA cubed, and B is equal to negative 3 over 4 W times A. So keeping in mind the previous boundary conditions and considering that the general solution for phi, we get the final equation for phi. So using integration, we integrate the momentum equation, and we can find the pressure being exerted on the liquid. So below that is the equation for pressure. By integrating the shear stress equation, we can find the drag force. So the following equation relates to shear stress. You can see right there. By integrating the pressure equation, we can find that the force in the z direction due to the pressure field is the following equation of F. And then we can find that the force in the z direction due to viscous shear stress is the following equation for force due to shear stress. So by adding the forces due to pressure and force due to shear stress, this yields the total drag forces, which allow us to get the Stokes part of the Stokes-Einstein equation, which is equal to 6 times pi times a times u times mu. Now we go to the Einstein part. So the mean square displacement is a measure of the deviation of the position of a particle with respect to its reference position over a set time. So MSD is the time of t is defined as the following relationship. MSD is used as a displacement in the diffusion coefficient equation, which see the equation down below of d. The displacement of the particle coefficient can be expressed as an integral. So u is equal to velocity, and we are integrating with respect to time, so the lower and upper boundaries are 0 and t. as you can see in the equation below, and then the displacement integral is then plugged into the diffusion coefficient equation to get the equation for the integral. Boundaries and manipulation help us change the integral to be a function of time difference, so that way we can find the difference between 2 points in time. Once again, looking back at the equation of d, if we assume that 0 is less than time of point 1, which is less than time at point 2, and which is less than t, the diffusion coefficient can be simplified to the following equation for d. It's just a simple integral. So the diffusion coefficient equation is further simplified by rearranging the mobility equation, where we multiply said equation on top of the integral times 1 over k sub b times temperature in Kelvin. So finally we get f equals 6 times pi times u times 8 times mu over up to the negative 1 power. So rearranging it to solve for d, we get the following Einstein and Stokes equation, which is d is equal to k sub t b times t temperature in Kelvin divided by 6 times pi times u times 8 times mu. Thank you very much.